So in this presentation, we are going to look at cyber-physical system modeling. And let me give you a brief intro about what that means. If you think about what an asset management system or an asset inventory contains, you would probably first of all think about information about all those individual devices, which is what you would see in OTbase in the OT devices inventory. This is what this table here is called. And for any specific device, you can get the details. Well, all that's nice and dandy. However, there's one problem associated with that. For many use cases, the individual device or the atomic view is really not enough. You need to understand how devices interact, how they form groups, how they form systems. And I mean, that's not a new insight, because whenever you talk to a control engineer, for example, they tell you about their DCS systems, just as an example. They talk about machine lines, they talk about production lines. And this higher level view is super important and interesting for OT asset management, because just for one aspect of it, this is the entry towards any criticality analysis, right? Criticality is usually not associated with one single OT device, but it's associated with a system. That means if any part of that system goes down, well, then you have a problem. And what you try to do is you want to isolate that problem within that system. In other words, we are talking about a very practically important matter, which would be the basis of your network segregation strategy. And why would you need a network segregation strategy? Well, because patching doesn't work so well in OT, so therefore you need compensating mitigation, and the best shot that you got is network segregation and access control. So now here's the thing. You can approach your network segregation strategy on with a very dumb approach that only looks at horizontal layers. This is what many people get wrong when they get carried away with the Purdue model, right? The Purdue model is horizontal. But if you would use that as a strategy for network segregation, you might end up in a totally counterproductive environment. Right? Because if everything is segregated horizontally and any of these layers is compromised, then the whole joint will go down. That's not what we want. So the goal of any segmentation strategy is that you can localize the cost of compromise. And one way to get there is to understand how your various cyber-physical systems are structured and how they work together, how they are interdependent. And this is what this simple device list does not show you. It can give you all the details about an individual device, but you don't see any relations. Now, this is what we have changed in OTbase with the systems inventory. Okay? So that's another table where the entries that you see here no longer represent individual devices, but they represent systems. That system could be a conversion line. It could also be a water purification plant, as an example. Doesn't matter, right? And also, one thing is important to understand. None of these entries here are automatically generated. Sorry, OTbase doesn't know. But OTbase gives you a means to model those relationships. And we highly recommend that you do, because by doing that, you will get a superb technical documentation of your OT infrastructure and of your whole production environment, where you can finally, after all these years, really see all the relationships and dependencies. So let's see how that looks like. The first thing I would like to point out, very important, this is actually a hierarchy. So you have a couple of entries down below. They're just flat. But let's look at the more interesting systems up here. You can see I can open these entries. And then I see, oh, you know, there's something more. There's something below that. So, for example, in this flat rock site here, I see 3 different systems. One of these systems is called BIW15. That would be the body and white building or plant in that hypothetical automotive facility. And within that particular building or subcomponent, I see I have yet another layer of subsystems, right? And if you happen to be associated with automotive manufacturing, you say, oh, okay, I see, I understand what that means, right? So this is the body and white production part, and then I have the a subsystem for the deck lights. So in other words, we're pretty much talking about production cells here. This is the cell level, okay? And you can associate those individual components of the system with your devices. Let's see what that looks like. So once that I open a device profile, a system profile for any of these subsystems, I would see, oh, this is where all the devices are physically located in this floor map. And then further down, I see all the networks that are part of this system, and I see the various endpoints, the various individual OT devices, and I can also see the cells where they belong to. And the other thing that I can do is, with my network topology, you may have seen that already. In OTbase, we automatically create network topology diagrams. And when you use the more elaborate topology dialog in OTbase, let's do that rather quickly. This is where you have the opportunity to change the layouts to physical location, to system association, etc. Then you can now see how the OT devices are associated with those different cells. And then you could also see the whole network infrastructure. So, for example, when you would be interested in what connects which, you can always do that. Just hover over an individual component and you see the connections for that component. And as you see, this gives you quite a solid foundation for a segmentation strategy. On the other hand, if I would remodel the same network infrastructure in a Purdue fashion, just a click of the mouse in OTbase, it will look like this. What are we going to do with this? So just briefly, we use color codes to identify different device types. So everything in red is actuators, like in this case VFDs. And then you're in violet, you have your layer 1 with all the PLCs, and then up there you have the HMIs. Okay, so that's your Purdue model, right? But what does it actually yield when it comes to when you want to design a security architecture? Not much, right? Whereas this system view gives you much more grip on how to actually go about your segmentation. The other thing that I want to show you, and I'm using a different system for that, is how you can now also model the relationships and the dependencies. So let's look at this other system. In this example, we have chosen to model a power plant. So let me zoom in here a little bit. Oops, a little bit tricky with the trackpad here. Oh, damn. Yeah, I would like to have a mouse wheel for this, but I don't. So here you would see we have a power plant with 2 units, 1 and 2. Here we have our turbine. Here we have an electric generator. We have transformers, a condenser, steam generator, feed water system, and a control system. Okay, and the interesting part is that you can now model your dependencies. And you can just use various visualization alternatives, right? So for example, in this case, we have chosen to model electrical energy in red, whereas all the water-related circuit here that is modeled in, that is visualized in blue, okay? So that it makes obvious sense to the engineer. This is where they can relate to. And then you can add your control dependencies so that anybody could see, okay, my control system, in this case, Siemens SPP AT3000, it is directly controlling the transformers and the electric generator. And then we have a turbine control system that's embedded here, and we have a turbine protection system that's embedded there. Okay. The interesting thing about this this visualization is that it's also fully dynamic, so I can zoom in and out, and I can also close different parts of it. So if I would say, well, I'm not interested in Unit 2, I just want to focus on Unit 1, I can do that and just redraw the layout so to accommodate the use case that I'm presently working on, right? Let me give you another example, different system. Let's just look at a production facility in the food and beverage industry where I chose to model a filler line for what could be yogurt, for example. This is a little bit more complex. You know, power plants are very simple in structure. It's all about boiling water. And in this case, we have this, the process goes like this. So here I have the raw material handling, where it all starts. And the raw material goes into this mixer unit, this mixer subsystem, if you will. And as you can see, this is redundant. Okay, I have 2 preprocessors, then I have 2 reactors and 2 tanks. And from there, the material goes down here to the filler. Again, if I want to take a more bird's eye view, I can simply close these subsystems, and then it looks a little bit different. Depending on the use case, it might be easier to understand. Okay, and so here we have filled bottles that go from the distributor to the tray packer, etc. And for anything I want to do, I can change the layout depending on what I want to focus on. Down here we have a quality inspection. So I can document where the dependencies are. And this is going to be extremely helpful for determining system criticality. This is going to be extremely helpful to identify scenarios where I would say, well, wait a second, here we have some redundancy, and if you're just stupid, we will not take advantage of that redundancy, right? This happens actually quite often because, as you know, these cyber-physical dependencies are usually not documented. And this is what we want to change. And now in this new version of OTbase, it's actually possible, and in quite a very simple manner, because now you can document with granularity where the dependencies are and what those dependencies are. And as you see, they are not limited to cyber dependencies. They also include physical dependencies, which is super important because that is what separates OT from IT. I mean, in IT, you don't need a seasoned engineer to educate you about criticality, right? In IT, well, maybe if you've worked in the field for 2 or 3 years, you know already, well, you know, that big database server, that is important, that is critical. Whereas the workstation for let's just say, the guys in the legal department, they are not so critical, because if they all go down, you can still produce your product and can still generate revenue, right? And so that's why these physical relationships, that's why a process understanding, an understanding of the physical process is so super important. So I would put it this way: if anybody tells you about cyber risk, usually it's just a totally vague idea. It's just hanging in thin air. If you really want to understand your risk, where it is in your plant, where it is built in, where it is designed in, you must go to this deeper level of cyber-physical modeling. And you would also need to do an exercise which would be similar to a FEMA analysis, where you really go through with the SMEs, with the subject matter experts, with the engineers, and just do that as a tabletop exercise. Well, what happens if this component fails? What happens if the control system for this component is compromised, if it goes down or it just malfunctions, right? And the good news is usually the SMEs can answer those concrete questions rather easily. And now you have the tool to put it into a model, right? And that model is going to go a long way when determining your criticality and your mitigation strategies, your prioritization strategies, because all of a sudden it becomes pretty clear what the critical components are. And this helps you to address maybe the most fundamental problem in OT security, which is you will never have enough budget and time. You always need to heavily prioritize, right? So therefore, your measure of success would be, did I focus on the right topics, on the right systems, right? This is at the end of the day where the rubber meets the road. Did you spend your small budget that you have intelligently? Did you really max it out, right? This is all about prioritization. And in my opinion, you cannot make it happen if you don't have a very good understanding and documentation of those cyber-physical dependencies. And this is why we have added this functionality to OTbase so that it finally is usable, right? Yeah, so that's something that you can now take advantage of in OTbase. Just to make it concrete, you could also filter any of these relationships. I could say, no, I'm not interested in the material flow for this analysis at this point in time. So let's just disable that. Let's just focus on the cyber dependencies, right? So you can also do this filtering on a visual layer, and you can just resize it and relay out it in whatever way you seem fit, just to address the use case at hand, to address your present analytical needs. Okay, any questions about that?
So, do you have to spend time developing, or what sort of inputs come in from the tool? How do you model this?
How do you model this? Yes, that is very simple. Let me show you. So the usability is very important. I get that. So let's take this system right here that we have just looked at. This is the hierarchy that you have just a second ago seen in visual form. And let's just say I want to add a component. I could say, well, in that aromatics dispenser, I have an additional subcomponent. Well, then I just select that aromatics dispenser and click on Add. Okay, now I can add that subcomponent. Let's just say aromatics dosage subsystem, ADS. Done. Okay, there it is, down here. But now I also want to express any relationships. Good. Maybe it is not really a good example, but just to show you how that works. So I can go to the Edit dialog, and down here I can now define the relations. And the relations always have a direction. So it's either consumes from or provides to, right? Provides to or consumes from. This is the direction of the relation. Where it's a question, where does the arrow point to? So let's just say I say consumes from. Now I can select any of the other systems.
So we'll just
Spartanburg, and I just use a silly example here. I use the preprocessor 1 from that mixer. Then I can select a relationship group, and I think if you look at these that are pre-populated, well, it makes obvious sense, right? You would expect to have a category for material flow, for example. You would expect to have a category for HVAC, for logistics, right? But the thing is, you can totally define your own process groups or categories or relationship groups, right? So this is editable, and you can also assign the color codes that you like. We don't care. You can assign the line size. You can say, well, this should be a dotted line, right? This should be a solid line, because we want to allow the user to use existing corporate standards if they have them, right? We don't want to impose any new standards in that field. So let's just say this is another conditional material thing, and I can add a more detailed description, right? So I could say, well, this is about the aromatics dosage specifics. Okay, done. Good, save. And now if I look at the system again, let's look if we can identify any changes. Oh, it's difficult here with that stupid touchpad. It doesn't make it easy for me. Preprocessor, come on. There you go. Right? So here you see that that's the subsystem now of this aromatics dispenser, and the relationship is also exposed here. Right? And if we would say, oh, we just exclude anything else, do another layout, it's easier to see, right? So, but I mean, the point of this exercise was to show this takes you 5 minutes, right? And the other thing that's probably important to understand, that this is not just a graphics thing, right? So it's really about the data. Now you have it in the database, you can expose it via the REST API, and you can run analytics on it. That is going to be the next step, right? So that you can analyze critical dependencies algorithmically. I mean, it's nice that a human expert could tell you, oh, I'm not sure if that's a good idea. So for example, customers already told us, well, we have identified dependencies that actually are not even necessary, right? That's nice, but it's even better when you don't need a human SME, but that this can be exposed via software, to make sure that you don't miss any critical dependencies that would call for a different type of instrumentation and control, right? So this is what cyber physical modeling is all about in OTbase Inventory 8.1.